Imagine a high-security banking facility, right?
Hmm.
You've got biometric scanners, armed guards, a 3-foot-thick steel vault door.
Oh, yeah.
But then if you just walk right up to the terminal and, I don't know, input the word error in a specific font, the system just defaults to unlocking the gates.
That is exactly what we're looking at today. It's wild.
Yeah, welcome back to Cyber Warnings Daily. This is your high signal briefing right here on the deep dive. I'm super excited to get into this one.
Yeah, me too.
Because whether you are actively hunting threats on an incident response dashboard or, just reviewing your network architecture over a coffee, you really need to hear this one.
You absolutely do.
Today, we are dissecting a pretty terrifying wave of vulnerabilities where attackers don't even need to steal a password. Like, they aren't phishing.
No credentials at all.
Right, they were just bypassing the front door completely, using these really simple logic flaws to gain unauthenticated access.
It is, it's the kind of threat landscape that makes you rethink your entire perimeter defense, honestly. Because we are tracking 3 distinct disclosures today.
Right.
And while they impact completely different layers of the modern tech stack, so moving from, enterprise middleware down into widespread application plugins, and then finally into the core identity management vaults themselves.
Actual vaults, yeah.
Right. But the narrative through line here is undeniable. We are looking at the incredibly fragile nature of authentication logic.
Okay, so let's unpack this.
Yeah.
Our mission for today's deep dive is to break down the mechanics of why these unauthenticated access flaws exist.
Yeah.
And we're going to strictly focus on the actions you need to take as a defender.
That's the most important part.
Right. So let's start at the enterprise layer with Oracle.
Okay.
We have this severe vulnerability. It's tracked as CVE 2026-2019-62. And this is impacting the Oracle HTTP server and the Oracle WebLogic server proxy plugin. And what's crazy is this one sits at an absolute maximum on the CVSS severity scale. It's a 10.0.
Yeah, a perfect 10 is never what you want to see in a vulnerability report.
No.
Especially when it involves enterprise middleware. I mean, the sources indicate that this allows an unauthenticated attacker, so someone with just network access via a simple HTTP request, to completely compromise the servers.
Just a standard HTTP request.
Just HTTP.
Yeah.
And it leads to unauthorized access or even modification of critical data.
I really want to dig into the actual mechanism here. Because a 10.0 implies total failure of the system.
Total failure, yeah.
So when we talk about an unauthenticated attacker using standard network traffic to escalate to system compromise, how does that handoff actually break? Because the proxy plugin is basically the trust boundary between the public-facing web server and then those heavy-duty internal WebLogic applications. So if I'm just firing a regular HTTP request at it, why isn't it demanding credentials before letting me touch the back end?
Well, that trust boundary is exactly the core of the issue here. To understand the mechanics of a flaw like this, you really have to look at how middleware parses incoming traffic. So the proxy plugin is designed to take an incoming HTTP request, parse the headers, make a routing decision, and then basically forward it to the internal WebLogic server.
Right.
But because it's a proxy, the internal server inherently trusts the traffic it gets from the plugin.
Oh, because it assumes the plugin already did the checking.
Exactly. The vulnerability resides in the component that processes that initial request before the authentication check is fully enforced.
So wait, if the proxy's parsing logic is flawed, maybe it, I don't know, mishandles how the request is formatted, or it fails to sanitize the routing path.
Yeah.
It basically just rubber stamps the malicious payload.
Precisely. It rubber stamps it. Now, the sources don't release the exact proof of concept payload, which is pretty standard for something this severe.
Right. You don't want to hand them the keys.
No, exactly. But the mechanical failure in these kinds of proxy bypasses, it usually involves the attacker crafting a very specific request that exploits that routing logic.
So they trick the proxy.
Right. The proxy misinterprets it and assumes it doesn't require authentication based on that flawed parsing.
Wow.
And then it just blindly forwards it into the internal environment.
And the back-end server just sees it coming from the trusted proxy.
Yeah, the backend is like, oh, the proxy sent this, it must be fine, and it just executes it. You slip right past the perimeter because the system processing that very first handshake is fundamentally broken.
Perimeter just dissolves completely.
It's gone.
And looking at the timeline in our sources, there's this massive, why it matters gap here.
Yeah.
Because Oracle released patches for this specific flaw back in January.
Yes.
We are now months downstream from that release. So if the patch has been out for over half a year, Why is this suddenly a 10.0 emergency today?
Well, the timeline is actually the most alarming part of this whole thing.
Really?
Yeah, because threat intelligence reports from organizations like Greynoise and CloudSec, they're currently just lighting up with activity.
Oh,
They monitor the background noise of the internet, right? The automated scanning and probing that attackers do constantly.
like the bots just pinging servers all day.
Exactly. And those sensors are showing active, really aggressive exploitation efforts right now. Attackers are actively scanning for unpatched instances of WebLogic.
So they are essentially betting that complex enterprise environments just haven't managed to patch their middleware yet,
Yeah.
even though the fix has been out since January.
And it's a highly successful bet.
Is it really that slow?
Oh, yeah. Patching enterprise middleware like WebLogic, it is notoriously complex. It often requires scheduled downtime. You have to do extensive regression testing to make sure you don't break legacy internal apps.
Oh, right, because if you break the app, the whole business stops.
Exactly. You have to navigate a lot of change management bureaucracy. And attackers know this life cycle. They wait for someone to reverse engineer the patch, create a reliable exploit, and then they cast a massive net.
Which totally explains why the government has stepped in now. Because CISA, the Cybersecurity and Infrastructure Security Agency, they formally added this to the Known Exploited Vulnerabilities catalog.
Right, the KEV catalog, which is basically the definitive mandate for prioritizing your patching queue.
Yeah.
And for defenders listening, this comes with a hard legal deadline. Under Binding Operational Directive 2604, federal civilian executive branch agencies are required to apply the fixes for this Oracle flaw by August 27, 2026.
August 27.
Yeah.
I mean, even if you aren't managing a federal network, that date should be circled in red on your calendar.
Without a doubt, the KEV is the gold standard for threat prioritization. If CISA issues a binding operational directive for it, it means the exploitation is severe, it is widespread, and the damage is real right now.
So what's the immediate action item here?
As a defender, your immediate action is extremely clear. You must identify every single instance of Oracle HTTP server and the WebLogic proxy plugin in your architecture.
Check the logs.
Audit your patch logs exactly. If that January patch is still sitting in an IT backlog somewhere, you have to deploy it immediately. And if you have legacy systems that absolutely cannot be patched today, you need to severely restrict network access to those proxy endpoints.
Cut it off.
Cut them off, yeah.
Okay, so we have attackers heavily scanning the perimeter for unpatched middleware, but attackers are opportunistic.
Yeah.
They aren't just stopping at the enterprise level, right? Once they realize organizations are struggling to patch deep stack routing like Oracle, their automated scanners just immediately pivot to the application layer.
That's right.
Which brings us to a massive disclosure impacting WordPress.
Yeah, the easiest path to high privilege is often through these ubiquitous, broadly installed web plugins that handle authentication.
The stuff everyone uses.
Exactly. And the mechanics of this next vulnerability are just an incredible lesson in why cryptographic implementation is so incredibly difficult to get right.
Yeah, let's get into it because we are looking at a severe unauthenticated authentication bypass, which is a mouthful.
It is.
But it was found in the Securify miniOrange SAML 2.0 single sign-on plugin for WordPress.
Right.
And this is disclosed by PatchStack, who credited the DigitalOcean security team for the discovery. And the root cause here is described as a, quote, loose Boolean check, unquote, on the return values of a function called OpenSAMLVerify.
Yeah, this is where we get into the weeds of how programming languages actually interpret logic.
Okay.
So in PHP, which is the underlying language of WordPress, OpenSAMLVerify is the function used to check a cryptographic signature.
Okay, that makes sense.
When you implement SAML, the security assertion markup language, you are passing an XML document back to the application to prove the user has logged in via your single sign-on provider.
Right, the SAML response. It contains the user's identity, like the name is eyes,
Yes.
and a cryptographic signature that basically guarantees the data hasn't been tampered with.
Correct. So the WordPress plugin receives that SAML response, and it feeds the signature into OpenSAMLVerify just to make sure it's mathematically valid.
Simple enough.
And the function is designed to return an integer of 1 if the signature is valid, and a 0 if the signature is invalid.
Okay, 1 for good, 0 for bad.
Right.
But the sources note that the plugin failed to account for a third state, which leads to this loose Boolean check vulnerability. So I was thinking about this. Instead of a standard bypass, think of it like a broken polygraph machine, right?
Oh, I like that.
The attacker's signature fails the test. The needle swings wildly to error. But because the machine was only programmed to look for the word false, it prints out a pass.
The polygraph metaphor is highly accurate for what the PHP engine is actually doing here.
Oh, really?
Yeah, because the open stubble verify function returns a -1 if an error occurs during the verification process.
A -1.
Right. For example, if the cryptographic signature is completely malformed or missing key components, it throws a -1. And this is where PHP's historical type juggling becomes a catastrophic security flaw.
Okay, explain that type juggling, because how does a -1 error code suddenly become an admin pass?
So in PHP, if you write a loose Boolean check, meaning you use a standard equality operator rather than a strict equality operator that enforces both the value and the data type.
The double equals versus triple equals.
Exactly, yes. The language tries to be helpful. It evaluates whether the output is sort of truthy or falsy.
Truthy.
Yeah, truthy. So the code in the miniOrange plugin essentially asked, did this function return 0 for an invalid signature?
And because the function returned -1 for an error, the loose check just says, well, -1 isn't 0, so it must be a successful verification.
The math completely backs that up.
Oh.
Any non-zero integer in a loose PHP evaluation is treated as Boolean true.
Oh, wow.
So the system encounters a fatal cryptographic error, and the logic interprets that error as absolute success.
That is just mind-boggling.
It is.
So how does an attacker actually weaponize that in practice? Do they just drop the signature from the SAML response entirely, or do they have to specifically format the payload to trigger that -1 state?
They have to trigger the error state specifically. So an unauthenticated attacker would craft a fake SAML response XML payload.
Okay.
They set the name ID field to the target user, which is usually the site administrator.
Obviously.
Right. Then they purposefully corrupt the cryptographic signature data. They aren't trying to forge a valid signature. They are just breaking the math enough so that when the OpenSSL library tries to parse it, it basically chokes and throws that -1 error code.
And the plugin sees the truthy evaluation, completely ignores the fact that the signature was mangled, and just logs the attacker in as whatever user they specified in the name ID.
That's it.
Instant, unauthenticated admin access.
Instant site takeover. And you really have to consider the threat landscape here. The barrier to entry for this exploit is practically non-existent.
Because it's so easy to do.
Proof of concept code is already public. The exact same automated scanners hitting Oracle are also throwing these crafted SAML responses at every WordPress site they can index, just looking for that miniOrange plugin. You don't need to be some advanced persistent threat to execute this. You just need to run a Python script.
So for the defenders listening, the action item here is critical. If your WordPress architecture relies on the Securify miniOrange SAML 2.0 single sign-on plugin, you have an active, unauthenticated vulnerability just sitting on your perimeter.
Yes, you do.
You must update the plugin immediately.
Immediately.
If you are in a freeze period or you just cannot patch today, the mitigation is to disable the plugin entirely until you can. There is no middle ground here.
The risk of leaving it active is simply too high. Which actually brings us to the final layer of our briefing today.
Right.
Because we've seen how the middleware trust boundary fails. We've seen how application layer cryptography fails through logic errors. But what happens when the core identity vault itself, the very system designed to manage all this trust, is fundamentally flawed?
That is definitely the most concerning scenario, because if the identity provider falls, the entire ecosystem falls with it. So the sources highlight CVE 2026-8963. And this is a critical security flaw in Keycloak, which is the massive open source identity and access management server backed by Red Hat.
Huge footprint.
Right. And this vulnerability carries a CVSS score of 9.1 and is classified as CWE 640, which basically signifies a weak password recovery mechanism for a forgotten password.
Keycloak is often the single source of truth for an organization. It manages the SSO for dozens, sometimes hundreds, of internal and external applications.
Yeah.
Taking over an account here is the very definition of a catastrophic breach.
The root cause in the sources is listed as improper state validation within the reset credentials authentication flow. And apparently, this allows an unauthenticated remote attacker to take over any account.
Any account at all.
Now, I want to bypass the basics of what a password reset is, because we all know the standard flow. You forget your password, you click the link. What I want to understand is the state machine logic. How does an attacker actually hijack a reset flow to override a different user's state without ever having to intercept the victim's email or session token?
You are hitting on the exact trust mechanism that fails in this vulnerability.
Okay.
When we talk about state validation in distributed systems, we're talking about how the server tracks a user through a multi-step process.
Right.
In Keycloak, when a password reset is initiated, the server creates a state. It's an internal tracking session. It has to map the initial request for a specific user ID to the subsequent actions, like verifying the email token and then finally submitting the new password.
Right. The server has to remember that the person submitting the new password in step 4 is the exact same person who clicked the link in step 2.
And that is exactly where the state validation breaks down.
Oh, really?
Yeah, the application logic doesn't strictly bind the state ID to the initial requesting user throughout every single transition. The server effectively just loses track of the context. So an attacker can initiate a password reset for a highly privileged target, say a domain administrator.
Okay.
The Keycloak server starts the flow and creates a state for that admin.
But wait, the attacker doesn't have access to the admin's email, right? So they can't click the verification link. How do they force the state machine to just skip ahead?
Because the state validation is weak, the attacker can manipulate their own concurrent session or inject specific parameters into a POST request that confuse the server.
Okay, see.
They basically send the final update password payload, and because the server's state tracking is desynchronized or poorly enforced, it applies that final step to the open state of the targeted administrator.
So the attacker leverages the server's own confusion.
Yes.
The server sees a valid password update request coming in, looks at the open state flows, and just blindly applies it to the targeted account, completely bypassing the cryptographic email token verification.
That's the core of the issue. It is a complete failure of the state machine. The server forgets who it is talking to midway through the conversation. And the attacker overrides the legitimate user's credentials with ones they control, gaining full access to the Keycloak identity.
And once you have the Keycloak identity,
You have the keys to the kingdom, you have the HR portals, the cloud infrastructure dashboards, the code repositories, literally everything tied to that SSO environment.
it is a devastating logic flaw. And again, it requires zero prior authentication. You just need to be able to reach the Keycloak login screen.
Just network access.
So for the engineers and architects managing identity infrastructure, what is the strict defender mandate here? Because we need to know what to do.
Managing identity infrastructure requires absolute precision with version control, and this patch cycle has to be a top priority.
Right.
If you are an open source user running upstream Keycloak, you need to verify your deployment and update to version 26.7.2, which was released on August 19th, 2026.
Upstream Keycloak version 26.7.2.
Exactly. Now, if your organization is utilizing the enterprise track, the Red Hat build of Keycloak, which is known as RHBK,
Right.
you have specific update paths based on your current deployment. You must apply the updates shipped for either version 26.4.15 or version 26.6.7.
Okay, got it.
You simply cannot afford to leave your identity provider exposed to an unauthenticated state manipulation flaw like this.
No, absolutely not.
Yeah.
Well, let's synthesize this briefing. We've covered a massive amount of technical ground today.
We really have.
We analyzed how Oracle WebLogic's proxy parsing logic fails, which allows attackers to route unauthenticated HTTP traffic directly into the backend. We broke down the WordPress miniOrange SAML flaw, where a loose PHP Boolean check turns a cryptographic -1 error code into full admin privileges.
Yeah, that truthy check.
Right. And we just explored how Keycloak's state machine can be manipulated via parameter injection to hand over any account during a password reset.
The connecting thread across all these sources is a stark warning.
Yeah.
Whether you are defending enterprise middleware, managing web application security, or architecting identity vaults, your immediate priority today is reviewing these unauthenticated access vectors. Check the perimeter.
Check your KEV compliance, audit your PHP plugins, and verify your Keycloak builds.
It fundamentally changes how you look at perimeter defense. I mean, you don't need a stolen password if the application logic simply invites you inside.
Let's take that a step further, actually, because the nature of what we discussed today really challenges our industry's focus.
How so?
Well, we spend an incredible amount of time and budget worrying about advanced, persistent threats. We model scenarios for zero-day kernel exploits or highly sophisticated AI-driven phishing campaigns.
Is it the flashy stuff?
Right, exactly. But the reality presented in these disclosures is much more systemic.
The threat isn't always a highly complex cyber weapon.
No, it isn't. The most devastating breaches we are seeing right now stem from simple fundamental logic errors.
Just bad logic.
A proxy server that inherently trusts unvalidated headers. A programming language that evaluates a mathematical error as a success. A state machine that simply forgets which user it was authenticating halfway through the process.
These aren't advanced hacking techniques. They are failures in the very basic mechanisms designed to verify who we are.
It's a really sobering realization for anyone building or defending these systems.
It really is. And I want to leave you with this thought to mull over as you analyze your own network architecture today.
Okay.
If the fundamental locks of our digital infrastructure are failing at this basic logic level, it begs the question, are you focusing too much budget on building taller walls while ignoring the fact that your front doors don't actually know how to recognize a key?